All right, today we're diving into a really fascinating question. How do we find the hidden patterns in the world all around us? And to kick things off, I've got a bit of a riddle for you.
I know, it sounds like the setup to a really weird joke, right? But believe it or not, there's a deep structural connection linking all of them. And figuring out what that is, well, that's the key to making some absolutely incredible discoveries.
The answer? It turns out they all exist in what scientists call special two-sided networks. Now, you might also hear the term bipartite networks. It's a pretty simple idea on the surface, but it has some really profound consequences for how we find meaning in all kinds of data.
So first things first, let's get a really solid grasp on what exactly makes these networks so special.
Okay, so a bipartite network has one really fundamental rule. Imagine you have two totally different sets of things. Let's call them Group A and Group B. The rule is super simple. A connection can only form between something from Group A and something from Group B. Things in Group A can't connect with other things in Group A. Same for Group B. They can never connect to their own kind. And once you start looking for this structure, you see it everywhere. I mean, think about it. An actor connects to a movie, right? Not to another actor. A bee connects to a flower, not to another bee. A customer connects to a product they buy, not to another customer. These two-sided relationships are just all over the place.
Okay, so once we can see these networks, the obvious next step is to try and find interesting patterns inside them, right? But, and this is a big but, this is where things start to get really tricky.
See, a huge goal in network science is to find what we call communities. And that's just a fancy word for groups of things that are way more connected to each other than they are to everything else. You know, like a specific genre of movies and the small group of actors who always seem to pop up in them. That's a perfect example of a community.
So here's the puzzle. How in the world do you find a tightly knit group when its members are made of two completely different kinds of things? Remember, an actor can't directly connect to another actor, so all our usual ways of finding clusters and groups, they might just fall apart.
And that right there is the core problem this research paper tackles. A lot of the standard tools, the algorithms we use for this kind of analysis, are basically one size fits all. They treat every network as if it's the same, completely ignoring that strict no same-side connections rule. And as you can probably guess, that can cause some major problems.
So to really see why this is such a big deal, let's put two different approaches head-to-head. You can think of it like a showdown. We've got the generalist, who kind of knows a little about everything, versus the specialist, who is an absolute expert in one specific thing.
First up is our generalist. Technically, it's called the Newman-Girvin, or NG model. This is your standard, off-the-shelf, one-size-fits-all tool. And its core assumption is that, in theory, any two things in the network could be connected. It is completely, totally blind to that special two-sided rule.
And then we have the specialist. This one's known as the Barber, or BB model. And this thing is custom-built for the job. It has that bipartite rule baked right into its DNA. It knows from the absolute get-go that an actor can only connect to a movie and never, ever to another actor. So here's the bottom line, the fundamental difference between them. The generalist model wastes a ton of energy thinking about connections that are literally impossible in this world, like trying to calculate the odds of one actor connecting to another. It just can't happen. The specialist model, on the other hand, is way smarter. It only bothers with connections that could actually exist. It's really that simple. One model respects the built-in rules of the data, and the other just plows ahead ignoring them.
Okay, so the theory sounds good, right? But the real question is, which one actually works better in practice? Well, the researchers decided to find out by putting them head-to-head in a couple of tests. So for the first test, they did something really clever. They created a totally artificial network where they already knew what the right answer was. They basically built a little world with very clear, predefined communities. Think of it like creating a test where you already have the answer key. This way, they could see which model was better at finding those planted groups.
And the results? Well, they were pretty striking. This chart basically shows how forgiving each model is. The generalist model only found the right answer in this tiny, narrow window. You had to get the settings just right. But the specialist model? Look at that. It found the correct communities across a much, much wider range of settings. It wasn't fussy. It was just way more robust and reliable. And the researchers themselves put it perfectly. They basically said that when you build your model using as much information as you have about the system's rules from the very beginning, you just get better, more trustworthy results.
In their words, the detected community structure is much less sensitive to the choice of parameters, which signifies the importance of constructing the null model term using as much information as possible.
All right, so the specialist model clearly won the clean, controlled test. But what about the real world, with all its messiness and complexity? To find out, the researchers unleashed it on a real-world network, a map of all the languages in the world and the countries where they're spoken.
So the specialist model gets to work crunching all this data, and then it finds something really specific. It found a sharp, clear signal suggesting the world naturally divides into about 120 distinct groups.
Now this is a huge deal. What the specialist model found suggests there might be a real structural division of our world into roughly 120 distinct linguistic and cultural zones. And the generalist model, because it was built on the wrong assumptions, it just completely missed it. It smoothed right over this incredible detail. The pattern was invisible to it.
So let's zoom out for a second, because this isn't really just about languages or complicated network models. There is a much, much bigger lesson here for how we should think about data and making new discoveries.
And the takeaway is a really simple but incredibly powerful three-step process. Step 1, take the time to actually understand the unique structure of your data. What are its fundamental rules? Step 2, choose an analytical tool that actually respects that structure. Don't just grab the first thing off the shelf. And step 3, you will be rewarded. You'll get more reliable results, and you'll be able to see hidden patterns that those one-size-fits-all tools would have completely blinded you to.
I mean, it's common sense, right? You wouldn't use a hammer to turn a screw. And it's the exact same idea here. Specialized problems need specialized tools. When we ignore the known rules of a system, we're not just being lazy, we actually risk hiding the truth from ourselves. The right model isn't just a little bit better. It can literally be the difference between making a discovery and missing it entirely.
And that just leaves you with a pretty big question, doesn't it? What other important patterns are we missing right now? In genetics, in economics, in social networks? How many huge, groundbreaking discoveries are just lying there hidden in plain sight, simply because we're using the wrong one-size-fits-all tools?